let us finish our discussion of section 3.7. Please take a look at, for example, this system. So once again, how we solve this system? Step 1, form augmented matrix. Apply elementary row operations in order to come up with an echelon form. The echelon form tells us that our system has infinitely many solutions. Why? Because, number 1, the echelon form does not have a row that completely consists of zeros except for the very last number. Since there is no such a row, our system has at least one solution. But why does it have infinitely many solutions? It's because the number of pivots, which is 2, is lesser than the number of variables, which is 3. So, once again, the echelon form tells us that the system has infinitely many solutions. In order to find all these solutions, we keep applying elementary row operations in order to obtain the reduced echelon form. After that, we switch to the corresponding system and we leave all basic variables on the left and we move all free variables, well, in our case we have just one free variable, x2, to the right. Here's a complete description of all solutions of our system. Now, you may ask me a question, how do we know which variable is basic, which variable is free? Well, we look at echelon form or reduced echelon form again. Note that pivots are in column number 1 and column number 3. Therefore, x1 and x3 are basic variables. Note that column number 2 is not a pivot column, therefore x2 is a free variable. But now let us continue. I want to show you the structure of the general solution of our system. Here's what we do. We start with boldface x. Boldface x denotes the general solution of our system. Since we have 3 variables, boldface x is x1, x2, x3. Next step, we leave all free variables, well, in our case we have just one free variable, without change. And we replace all basic variables by the corresponding expressions. Done, done. After that, we rewrite each entry of this matrix column in the following form: number plus number times variable. So we rewrite this as number plus number times x2. We rewrite this as number plus number times x2, and we rewrite this as number plus number times x2. Lastly, let us split this matrix column into 2 pieces. Piece number 1 plus piece number 2. Here's what is important. Column number 1 is a particular solution of our system. Here's why. Well, observe that x2 is a free variable. Free means we can plug in any number instead of x2, and the resulting expression will give us a solution again. For example, if you replace x2 by 0, the second term will disappear completely. But remember, no matter what we plug in instead of x2, the whole thing is a solution. So, if we replace x2 by 0, this term disappears. Therefore, what is left is this, and this is a particular solution of our system. Now, I claim that the second portion is the general solution, but not of this system, of the corresponding homogeneous system. Why is that? Homogeneous system means instead of 7 we have 0, and instead of 6 we have 0. So if we have 0 here and 0 here, and we want to find the general solution of this homogeneous system, we will put here 0 and here 0. Therefore, here and here, here and here, here and here will have zeros. Therefore, here we will have zeros. And here we'll have zeros. Therefore, instead of -5 and 3, we will have zeros. Means, if instead of non-homogeneous system, we'll have the corresponding homogeneous system, matrix column number 1 will be the 0 column. Means we can ignore portion number 1, and therefore the general solution of our homogeneous system will be just this. Conclusion: what is written here is the general solution of our corresponding homogeneous system. So, repeat once again. If we have a non-homogeneous system, its general solution is the sum of two pieces. Particular solution of the system plus general solution of the corresponding homogeneous system. Same situation we have for any other system of linear equations. Here's example number 2. Again, we have a system of linear equations written in matrix form. Note that its general solution is the sum of two pieces, particular solution of the system plus general solution of the corresponding homogeneous system. This rule works even if the original system is homogeneous. Its general solution can be written as general solution of homogeneous system plus 0, which is the particular solution of our homogeneous system. Now, let us go back to one of our previous handouts, namely this handout. Note that a similar situation we had with linear non-homogeneous equations. The general solution of such an equation is again the sum of two pieces. General solution of the corresponding homogeneous equation plus particular solution of the original non-homogeneous equation. Therefore, question is why in two very different cases, systems of linear equations and linear differential equations, we have basically same structure of solutions. Answer is linearity. Since the left-hand side of our differential equation is a linear operator, the general solution of such an equation has this structure. Similarly, I am about to show that the left-hand side of our matrix equation is a linear operator. And this is exactly what I am about to discuss. The goal of today's class is to discuss transformations from Rn to Rm. I will show you an analog of linear operators that we discussed for functions. Remember, we discussed linear operators in this section, but these were operators on functions. Now let us discuss operators, and in particular linear operators, not on functions, but from Rn to Rm. So what is an operator on Rn? An operator T And here we have different words, transformation or function or mapping. It's a rule that assigns to each vector x from Rn a vector t of x in Rm. Here's an example. Let us consider a transformation from R2 to R3, which is given by this formula, where A is this. Question, what is T of U? U is this. Answer, T of U by this formula is A, U, and we multiply these two matrices together. Here is T of U. Note that T is from R2 to R3 because input is from R2, output is from R3. Now, as before, a linear transformation is a transformation that satisfies both properties. Let us show that this particular transformation is indeed linear. It is easy to show. T of xy by this formula is A times x plus y. We can expand parentheses, and then AX is T of x and AY is T of y. Similarly, we show that this transformation satisfies property number 2. So conclusion, if we consider a transformation from Rn to Rm, which is given by this formula, it is linear. Therefore, going back to our systems, a system of linear equations can be written in a matrix form, and now we understand that the left-hand side is a linear transformation. And one can show that thanks to linearity, the general solution of our system can be written as the sum of two pieces. Particular solution of our system plus general solution of the corresponding homogeneous system. Now, theorem 10 is of a great importance. We prove the following result. Suppose we have some linear transformation from Rn to Rm. Theorem 10 says that any linear transformation can be written as Ax. So compare this example and theorem 10. In this example, we say that if we have a transformation of this form, it is linear. Theorem 10, vice versa. If our transformation is linear, it can be written as Ax. Moreover, theorem 10 gives us an explicit formula for A. Column number 1 is T of E1, column number 2 is T of E2, and so on. Column number n is T of En. Example. Let us consider the following transformation from R2 to R2. Input is x, output is 3x. First, let us show that this transformation is linear. Well, it's easy to show. T of x1 plus x2 is 3 times x1 plus x2. We expand parentheses. Now this is T of x1, this is T of x2. In the same fashion, we check property number 2. Therefore, since this transformation is linear, we can apply theorem 10. And by theorem 10, our transformation can be rewritten as matrix times x. Question is, how do we find this matrix? Answer, theorem 10 tells us that column number 1 of our matrix is T of E1. Column number 2 of our matrix is T of E2. What is T of E1? By this formula, it's 3 times E1, which is this. Column number 2 is 3 times E2, which is this. Conclusion, our matrix A is of the form 3, 0, 0, 3. Folks, any questions here?
So each E column is just like E in the subscript denotes where the 1 is for that E column, right? So like E1 is the first row is where the 1 is and it's all zeros. And so
First of all, in matrix A, column number 1 is not E1, it's T of,
yeah,
where
so like,
E1 is this.
that's E1, okay, and that E sub n and so forth. So you just apply
Yes, absolutely, yes. So columns depend on T, but E1, E2, and so on are always same. This is E1, this is E2, and so on. This is En. Other questions here?
Is E always going to be that identity vectors, or can they be any vector?
No. Here we have to use the standard basis.
Okay.
E1 is this, E2 is this, and so on. Let me show you a pretty non-trivial application of this theorem. Please take a look at this example. Let us consider the following transformation from R2 to R2, namely a rotation. First of all, I am about to show you that when we rotate a vector about the origin, this is a linear transformation. This picture shows why property number 1 is true. Please take a look at this. Consider vector u and vector v. Obviously, this is u plus v. Now let us rotate the whole thing about the origin. We will get this. Well, then this is t of u because t is rotation. This is t of v, and this is t of u plus v because t is rotation. Observe that according to what we see here, t of u plus t of v is equal to t of u plus v. This picture shows that if t is rotation, property number 1 is true. In the same way, we show that property number 2 is also true. Conclusion: rotation about the origin is a linear transformation. Since rotation is a linear transformation, by theorem 10, this transformation can be written as A times X. How do we find A? Again, we use theorem 10. Column number 1 of matrix A is a rotation of E1. Column number 2 of matrix A is rotation of E2. How do we find coordinates? Well, please take a look at this picture. E1 is over here. Let us rotate E1 about the origin. We will get this. Now, let me show you that coordinate number 1 is cosine. Here's why. Coordinate number 1 is this distance. But know that by definition of cosine, this divided by 1 is cosine. Therefore, indeed, this distance is cosine, which is x coordinate. In the same fashion, we show that the second coordinate is sine because this is sine. So, t of E1 is cosine sine. It's column number 1. Lastly, in order to obtain column number 2, rotate E2 about the origin. Note that these are congruent triangles. Therefore, the y-coordinate of this point will coincide with the x-coordinate of this point. And the x-coordinate of this point is negative y-coordinate of this point because we go to the left. This is how we come up with column number 2. In particular, if phi is equal to pi over 4, the whole matrix becomes this. So if you multiply any vector from R2 by this matrix from the left, the resulting new vector will be a rotation of the original vector pi over 4 about the origin. For example, if we multiply this vector 1, 1 by this matrix, we'll get this, and it is easy to see that this new vector is a rotation of this vector about the origin pi over 4 to the left. Guys, before you ask questions, maybe I give you more examples of linear transformations. Please take a look at this. Input is x, output is same x, same thing. So t of x is equal to x. Is it a linear transformation? Yes, because one can understand that t of x can be written as identity matrix times x. Since our transformation can be written as matrix times x, it's linear. Here's a little bit more complicated example. Here's x, here's t of x. Is this transformation linear? Note that this matrix column can be rewritten as ax, where a is this. It's easy to check. Row number 1 times this column is entry number 1. Row number 2 times this column is entry number 2. Row number 3 times this column is entry number 3. So t of x is ax, therefore it is linear. Examples of nonlinear transformations. Here is x, here is t of x. One way to show that it's not linear is to observe that t of 2x is this, because we replace x1, x2 by 2x1, 2x2, and expand parentheses. On the other hand, 2 times t of x is this. We just multiply top and bottom by 2. Observe that t of 2x is not equal to 2t of x. Therefore, our transformation is not linear. It does not satisfy property number 2. Another way to show that this transformation is not linear is to come up with an example. Here is x1, here is x2. One can easily check that 2 of x1 plus x2 is not equal to t of x1 plus t of x2, because t of the sum is this, the sum of t's is this. Now, guys, questions?
The rules for proving linearity, very similar to proving a vector space.
Give me a second. So talking about vector space is a more complicated thing.
Right.
In order to show that it's a vector space, we have to check 10 properties, unless we see that our set coincides with the set of all possible linear combinations. You see it?
Right.
Linearity means condition number 1 and condition number 2. What is written here is similar to this, as we discussed, to this, which should not be a surprise. Here we have linear operators on functions. Here we're talking about linear operators on matrices. Does this answer your question?
Yeah.
Other questions?
And it has to satisfy both of those conditions, right?
Both, absolutely.
Okay, just make
Like linear operators on functions should satisfy both properties. Linear operators on matrix columns should satisfy both properties. Other questions? Lastly, please take a look at this. we say that a linear transformation from Rn to Rn, know that here we have same n. A linear transformation from Rn to Rn is said to be invertible if there exists a function s from Rn to Rn such that s of t of x is x and t of s of x is x. Here's what it means. X is an input. We act on x first by t, then by s. Nothing changes. Or first by s, then by t. Nothing changes. If such s exists, we call t invertible, we call s inverse of t. Lemma 2 says that if linear transformation t is invertible, then s is A inverse of x. What is A? It's the standard matrix t of x is equal to ax. Conclusion. Linear transformation t is invertible if and only if its standard matrix is invertible. Means if the determinant of this matrix is not equal to 0. Any questions here?
So the inverted transformation is equal to the inverse matrix times x.
Exactly. Once again, we start with a linear transformation. Note that by theorem 10, any linear transformation can be written as A times x. Now, lemma 2 tells us that t is invertible if and only if A is invertible. And the formula for its inverse is A inverse times x. And we all remember that A inverse exists if and only if determinant of A is not equal to 0. All right, guys, let me finish this section with a bunch of important theorems. Please take a look at lemma 3. By the way, on the next page, we discuss very important theorem that tells us how to determine whether or not vectors are dependent or independent. So once again, we put vectors together, come up with echelon form, and count the number of pivots. Now, if we put our vectors together and the resulting matrix is square, in order to determine whether or not these vectors are dependent or independent, we can also use lemma 3. Lemma 3 says that if matrix A is square and its determinant is not equal to 0, columns are independent. Moreover, it's if and only if statement, which means columns are dependent if and only if determinant is equal to 0. Going back to our vectors u1, u2, u3, v1, v2, v3. We put these columns together. We find this determinant by any method, and we see determinant is 0. Conclusion, vectors are dependent. For vectors v1, v2, v3, we put these vectors together. We find the determinant by any method. It is non-zero. Therefore, vectors are independent. So now, talking about dependence and independence, we have 3 different tools. Tool number 1, we can do dependence and independence by definition, as we discussed in this section, in section 3.3. Tool number 2 is this theorem. we put vectors together, come up with an echelon form, and count the number of pivots. And lastly, if we put vectors together and our matrix is a square matrix, we can use lemma 3. Let me finish this section with another important theorem. So please take a look at theorem 11. The equation ax is equal to b has a unique solution. X is equal to a inverse b if a determinant of a is not equal to 0. Of course, we can apply theorem 11 only if A is a square matrix. Sentence number 2. The equation ax is equal to b has either no solutions or infinitely many solutions if determinant of A is equal to 0. Therefore, corollary. The homogeneous equation ax is equal to 0 has a non-trivial solution if and only if determinant of A is equal to 0. Let me repeat once again. Suppose A is a square matrix. Consider the following homogeneous equation, ax is equal to 0. This homogeneous equation has a non-trivial solution, by the way, and therefore infinitely many solutions, if and only if determinant of this matrix is equal to 0. Folks, now questions.
Does that matrix have to be a square matrix?
Yes, it has to be square. Yeah.
Okay.